All right, geometry. We were going to make a video here for section 4.1. This is actually a little bit older. Most of the stuff we've gone past this, but hey, if you need to review, check it out. So the big idea today, we're going to be talking about classifying triangles. And when you're talking about classifying triangles, the big idea there is putting them into a category. What makes that triangle that kind of triangle? It's like, here's a dude that's purple with a red head and blue hair. I just classified him. Let's get into this. All right, so we got triangles all over the place. You look at this triangle here, we got triangles, triangles, triangles everywhere, triangles, triangles, triangles. We have triangles all over. Pyramids are made of a triangle. Houses usually have a triangle with them in the roof. Art has triangles in it, and you guys wouldn't believe how many places there are that have a triangle. The triangle is a very common shape in our world for lots of reasons. A lot of times for its stability and its simplicity. But let's just, look at some of these in how to describe. So, quick review, just some words that we need to talk about. For example, the word acute. Remember that acute means that we have an angle less than 90 degrees. And obtuse is something that's greater than 90 degrees. And a right angle is when it's exactly 90 degrees. So another thing that we have going on is how do we give it like sides that are congruent and such. So let's look at this first one. I got three angles and they're all acute. In fact, in a triangle you always have three angles, but they're all acute. And I also look at the three sides and those kind of look all different as well. So three different sides. So all the angles are unique, all the sides are unique. Then we call that an acute because that's the type of angles it has. It's acute and it's scaling. Scaling means that no sides match. Alright, let's look at this next one. This one's kind of the exact opposite. We got three angles that match. So it's three congruent angles. The sides, we don't know. And this is kind of an interesting thing because when we talk about, pardon me while I erase some of that there. When we talk about this type of triangle, we're going to call it equa, as in the same, angular. So we got equiangular. All right, and why is it equiangular? Because the angles are all the same, or they're all congruent. Similarly, we got this next one. We got 40 degrees, 50 degrees, but this is a big idea right here. So we got one right angle. Whenever you have a right angle, then it's going to be a right triangle. But we're going to add another word in here. We're going to call it scaling. Meaning that no sides are equal. Remember, if you need to ever pause this, run it at your own pace. This is your video. Run it at your pace. But I'm not going to slow down. So here we go. Next one. All right. What do we have going on here? We got an obtuse angle. We have an obtuse angle in there. So they're not all acute. We have one obtuse angle. And you can't have more than one, but we have one obtuse angle. I also look at the three sides and they don't look the same. I got 1, 2, and 3. None of them match. So no equal sides. That means it's going to be scaling again. So it's going to be obtuse and scaling. All right, this next one. Ooh. This side's 8.3, that side's 8.3, that side's 8.3. For that to work, that means that we have three equal sides, in other words, it's going to be equilateral. Actually, let's write that over here. It's going to be equilateral, because lateral talks about sides. Now, this is an interesting thing when we talk about equilateral or equal angular triangles. They're actually the same thing. It's kind of a secret, but they're the same. If I know that the three angles are equal and the three sides are equal, we call them more commonly, it would be called equilateral. But you can also hear it called equiangular as well. It's kind of interchangeable. Both words work. Let's look at another example. So I see that I have two sides that are equal, so two equal sides. And we have all acute angles. To me, that means that it's going to be an acute triangle. But because I have two equal sides, we have a word for that. It's isosceles. And if you didn't know how I just said that, think of it like this. I saw sillies. Isosceles. Let's look at the next one. We got three sides, none of them the same. So three different sides. That's going to be a scaling triangle. And just by looking at it, I can almost tell, but I'm not sure because I can't tell, is this a right triangle? I don't know. Is it a right triangle? Is it obtuse? Is it acute? I can't tell. So I'm just going to say scaling because I don't really know if that third angle in there is right, obtuse, or acute. That would be helpful if there was some marking or some angle measure, but I can't see it. So let's look at this one. This is like an official example, a very good example. You guys should take this one pretty seriously here. Let's look at this triangle EHG. EHG. So let's mark that in a certain color. How about blue? And we'll make very straight lines. So EHG is going to be from E to H to G, and G to E. And it has a right angle in the corner. That's interesting. So that's a right triangle. This is a right, whoops, let's make this in blue, take us back to north. That is a right triangle. How about EFH? How about red for EFH? That's going to take E to F. Let's make these lines. E to F, E to F, F to H, and H to E. Entirely hard to see, but this is actually an obtuse triangle. But it's because this angle right in here is going to be 120 degrees. How do I know that? Because the other piece of it's 60, and together those two pieces would make 180 because they make a straight line. So it's obtuse. Now the question, is it scaling, equilateral, or isosceles? If it was three sides equal, then that would be equilateral because they're all equilateral, and that's not it. If it was no sides equal, they're all different, that would be scaling. And it almost looks like that, but in fact it's not, because these two equal angles here, 30 and 30, that means it's going to be obtuse isosceles. Excellent. All right, let's look at the last one here. We'll do it in green. Or how about purple? FHG. That's this one here. FHG. So we're looking at this triangle. Now if I see that these two are 60, well the third one is actually going to be 60 up here as well, the third angle, because it makes a right angle which is 90 and part of it's 30, so the other part has to be 60 to add up to 90. That means I have 60, 60, 60. It's equa, or let's write this in purple for you guys so it's all color-coded, equa angular. Awesome. Okay, let's see what we got next. Now, what do I know? Well, okay, so I'm looking at this picture and I see that these two pieces are the same. And if those two are the same, anything that's the same, I can set equal to it. So then I'll have 4x minus 1.3 equals x plus 3.2. Well, let's work this out. I can add 1.3 to both sides. And I can subtract x as well. Then I'll have 3x on the left side, and these x's are gone. These 1.3's are gone. And 3 plus 1 is 4, 2 plus 3 is 5. So it's going to be 4.5. If I divide by 3, how many times does 3 go into 4.5? Let's see. 3 goes into 4 once. I'm going to subtract 3 because 1 times 3 is 3. 3 goes into 15, or 1.5, I guess you could say. 0.5 times. So our answer is 1.5. X equals 1.5. All right, well, let's try this one. This is going to be 1.5 plus 3.2. And so if I were to put that together, I'd get 4.7. Down here on the bottom, this is going to be 4 times 1.5 minus 1.3. But wait a second, these are the same. So I don't have to do all that work. I can just say it's 4.7. It's the same as the other one. The last one, though, I should work out. It says 5 times, then we got to plug in 1.5 for the x, minus 0.2. Well, that's going to be 7.5 minus 0.2 is 7.3. So those are my 3 side lengths. 4.7 for the 2 equal sides and 7.3 for the longer side. Okay. Let's keep going here. This one's very similar, very similar. Look at these two pieces. We got 2 equal sides and then a third side. The 2 equal sides, I can use those in the equations. I can set them equal to each other. 4x minus 10.7 equals 2x plus 6.3. So I got to do some algebra. Subtract 2x from both sides. I add 10.7 to both sides. In the end, I get 2x equals, well, we're going to carry a 1 here, and this is going to become 17. So when I divide by 2, x is going to equal 8.5. So let's look at these. This would be 2 times 8.5 plus 6.3. Well, go figure. 17 divided by 2 is 8.5. 8.5 times 2 is 17. So then I put those two pieces together, 17 and 6.3, and that would give me 23.3. So that's this side over here, this KL. That means the other side is also 23.3, the JK. Why? Because those are equal. That's what these two little marks mean, the tick marks. Let's figure out this last one though. 5 times x plus 2, that's going to be 5 times 8.5 plus 2. Well, 5 times 8.5, that's got a little more work involved there. Let's figure it out. 8.5, and let's multiply here. Stack it up. 5 times 5 is 25. 5 times 8 plus 2 is 42. Because I have a decimal in there, it's going to be moved over once. So that's 42.5, and then we're going to add 2 to it. So that's 44.5. There we go. All right, let's do some more. Ooh, look at this one. It says equilateral. When it's equilateral, that means all 3 are equal to each other. So I have options. This is different. There's more than one way I can set it up. I can either say 5y minus 18 equals 2y plus 3. Or I could say 2y plus 3 equals 3y minus 4. Or I could say 3y minus 4 equals 5y minus 18. It's up to you. I'll just start with the first one, but I could do any one of these and I would get the same answer. So let's work it out. I'm going to subtract 2y from both sides. I get 3y minus 18 equals 3. I add 18 to both sides. 3y equals 21. Divide by 3. Y equals 7. Excellent. So y equals 7. I'm going to plug it in. Let's do this first one here. 2 times 7 plus 3. That's 14 plus 3. That equals 17. So guess what? This one's 17, this one's 17, and the last one as well is 17. They're all the same because it's equilateral. Let's do a couple more here. When I look at this one, number 3, it says find the side lengths of QRP. Well, I see I have 3x minus 0.4 and x plus 1.4 and then x plus 0.1. 2 of those match. The third one does not. So which 2 match? It's this side here, RP, and this side here, RQ. So I'm going to have 3x minus 0.4 and x plus 1.4. So I'm going to subtract, x from both sides. I have 2x minus 0.4 equals 1.4. If I add 0.4 to both sides, 2x equals 1.8. Divide by 2, divide by 2. X equals 0.9. Okay. X equals 0.9. Cool. What do I do with that? Oh, I got to plug it in. That's right. Let's plug it in. Let's plug it into this one down here. 0.9 plus 1.4. Pardon the interruption there, you guys. I'm recording this video at school, and they forgot to make the announcement not in the classrooms. So, what were we doing? We were adding 0.9 and 1.4. You put those together, that's like 90 cents plus $1.40. That's going to be $2.30. 2.3. But wait, that means this is 2.3 as well because those two are the same. This last one is going to be 0.9 for x plus 0.1. Put those together and you get 1.0 or just 1. So there's our 3 answers. All right, for this last one, I have a feeling, yep, they are equilateral. Again, you have the options in here. We can say 4x plus 2 equals 3x plus 14. We can also say 4x plus 2 equals 5x minus 10. And we could even say 3x plus 14 equals 5x minus 10. Let's just pick one. How about this one right here? 4x and 5x. I'm going to subtract 4x from both sides. Add 10 to both sides. Let's see what we get. We get 12 on this side and x on the other. So 12 equals x. That wasn't too hard. Let's plug it in. 3 times 12 and then add 14. That would give me 36 plus 14, which is 50. So the answer is 50 for one side. But I know that they're all the same because they're marked as such. They're marked as being the same. So this side's 50 and this side's 50. That's awesome. Let's keep working our way through these here. Alright, lots of details in this one, but you got to realize that you don't really need everything. You just need the important stuff. Okay, a manufacturer produces musical triangles like this one by bending pieces of steel into the shape of an equilateral triangle. The triangles are available in side lengths of 4 inches, 7 inches, and 10 inches. How many 4-inch triangles can the manufacturer produce from a 100-inch piece of steel? Alright, let's figure out one triangle that's 4 inches. That means it's not just 4 inches, that means it's 4 by 4 by 4 because we have a triangle and on each side it's 4. So how much is the total usage for one triangle? That's going to be 12. It's the total perimeter. That's one triangle. So we have 100. There's a lot of ways you can do this. Let's say we had 2 triangles. That would be 24, because 1 is 12, so 2 is 24. 3 triangles would be 36, and so on. I could keep going. I could say 4 triangles. It's going to be 48. 5 triangles is 60. 6 triangles is 72. 7 triangles, pardon me, is 84. And 8 triangles is 96. And it looks like that's as far as we can go, because it's 9 triangles. We would need 108. And we only have 100. So that's not doable. Is there a faster way that I could have done this? You betcha. If I would have taken 100 and seen how many times can I push 12 into 100, well, it would have been 8, which would have given me 96, remainder 4. So I could make 8 triangles. Cool. Now the fact that it said 7 inches and then 10 inches, that's not a big deal. Those were irregardless numbers. It had nothing to do with what the question was. It was just asking how many 4-inch triangles can we make. Let's just do some practice. This was called the whiteboard practice on your worksheet, but we're going to work through it here. It says classify each triangle by its angle measures. Triangle ABC. ABC, this, I'm going to mark it in blue here. It's going to be ABC. Okay. Well, something interesting is happening. Notice that this is 30 and 30, which means together it's 60. We got 60, 60, 60. That is an equiangular triangle because all 3 angles are the same. 3 equal angles. BCD. So triangle BCD, I'm going to do that one in red. BCD is from here down to there, and then up there. Now if I look at this, I have a right angle here in the corner. That means that this is going to be a right triangle. And not just any right triangle, we're going to say right triangle and it's scaling because there's no equal sides. All right. Next. Keep on trucking. Classify each angle measure. Okay, we got 35 and 25, so that means together this piece is 60. That's going to be helpful to us later. And if this is 35 and this is 60, I'm going to give you a tip. This over here is going to be 85. And if that's 85, then this right there is going to be 95. And if that's 95 and 25, then this piece up here is going to be 60. So XYZ. XYZ, that means this bottom triangle, XYZ, that is acute because all the angles are less than 90, and it's scaling because they're all different. XYW, XYW, it's actually going to be equiangular because we have angular. We have 3 equal angles in there. We got 60, 60, 60. XZW is just the top triangle. That's scaling, but this time it's not acute, it's actually obtuse. So we've got to consider that. Why? Because we have this angle right here that's 95 degrees. It's greater than 90, so it's obtuse. Next, classify each triangle by its angle measures. Again, we keep coming back to this idea, so let's color code it again. We'll start with ABD. ABD is going to be A to B, then B to D, then back to A again. If I look at that, I have 100 degrees in there. And if that's 100 degrees, then I know that it's going to obtuse. And the 2 angles don't match, and this one up here is going to be how much? Not 40, 30. So that's going to be obtuse and scaling because nothing's equal, no equal signs. All right, let's do the next. ADC, so A to D to C and then back to beginning. That is a right triangle. So it's going to be right Let's see if we can get this right here. It's right, and it's scaling. BCD, BCD. That was 30. That means that this in here is going to be 60. That's 40, so that means this is 80. That piece in there, this one on the inside, BCD, is going to be acute and scaling. These are all scaling because there's nothing that match. There's no sides that match. What is the length of the longest side of the triangle? Okay, I'm guessing it's this one down here, but I got to figure it out by plugging in the pieces and checking them. Let's check. Okay, so we got 5x minus 9 and 2x plus 12. How do I know those are equal to each other? Because I see this tick mark and this tick mark. So I'm going to use that information to my advantage here. 2x plus 12 is going to equal 5x minus 9. They're equal because of the tick mark. So now I solve. I subtract 2x from both sides, and I got 12 equals 5x minus 9. I'm going to add 9 to both sides. Then I get 21 equals 5x. Whoa, not 5x, 3x. 3x. Divide by 3, divide by 3. 7 equals x. Let's figure out how big these pieces are. This is going to be 2 times 7 plus 12. That's 14 plus 12. That's 26. That means this side is 26 as well. Let's look at the bottom one. 6 times 7 minus 2. That's 42 minus 2, or 40. That's definitely the longest side. So what's the length of the longest side? The longest side equals 40. And that's it, you guys. That's kind of a summary of just an introduction, section 4.1 here. What have we done? We've classified triangles. And if things have tick marks, those little, that implies things that are equal. And then we can set up equations and solve and find measures. That's what we did. All right. Have a good night and watch part 2. Or not part 2, but 4.2. And we'll get even more interesting. Have a